Hello. Let's look at the case of an object which is going around in circular motion. Let's take a small block shown in yellow color of mass m tied to a string of radius r, and it goes around in a circular fashion. The radius of the circle is r. So we know that if we have to keep this object moving around in circular motion, then there is a minimum velocity that is needed to be given. The linear velocity shown here as Vd, which is for the down position, and the Vu for the up position. There needs to be a minimum value. Otherwise, if Vd is not having the minimum value, it cannot go all the way up to the top position. And same way, if Vu doesn't have the minimum value, it cannot continue to maintain its circular motion and reach all the way down. So let's try and find out what the values of Vd and Vu need to be, the minimum values, so that the circular motion can be achieved. Now if we look at it all the way at the top, the forces acting on the string are the tension Tu, which is the suffix for the up position Tu, plus mg of the object is also pulling it down. The tension is a pulling force pulling towards the center, and mg is pulling it towards the center of the earth. So these are the forces on the string. But we also know that for a circular motion, the force to pulling towards the center is called the centripetal force. So these two add up to nothing but centripetal force. Centripetal force is given by mv square by r. Vu is the suffix for the velocity at the up position by r. Now, if we look at this equation, there are constants like mass m is a constant, g is constant. The right hand side, similarly, m and capital R are constant, they are not going to change. So the only thing that I can change now is the velocity and thereby the tension. So if I keep reducing the velocity towards the minimum, if I keep reducing the velocity all the way down, at some point the tension will reach zero. Tension value would become zero, after which the rope would slack, the string would slack, and the mass would fall down and it would not go around in circular fashion. Now, which means the other way is that when the tension is zero, when Tu is zero, that is when I achieve the minimum velocity. That's the boundary point or the exact point after which it will not go around in circular fashion. The tension needs to be a little more than zero. To find the exact value, we can equate T equals zero. When T equals zero, the equation becomes mg equals mvu square by r. Now if we cancel out m and simplify this, we get the velocity at the up position, the minimum velocity that's needed at the top is square root of gr. This is the velocity that's needed at the top position for the circular motion. Now let's look at the position at the bottom here, down, all the way down. What needs to be the minimum velocity here again? Here we can use energy to find out. It's an easier way. So we know that energy is conserved in the system, or let's assume that energy is conserved in this whole system. That means wherever the object is, the sum of the potential and kinetic energies is going to be the same. Right? So now if we look at it at the top position, the energy here and the energy at the bottom down need to be the same. So if we look at the energy in the position up here, we have kinetic energy is half mv velocity up square. And the potential energy, if we take this as the reference point or the ground, then the object at the top here, up position, is 2 times the radius above. There is one radius here and height, and another radius height here. So 2r is the height, and we know that potential energy is mgh. So mg times 2r or 2mgr. This is the potential energy. So this is the potential energy, this is the kinetic energy, and this is for the position all the way up for u. And we also know that at the position down here, we do not have potential energy because we have taken the dotted line shown here in green as the reference point. So the height there is 0. So mgh becomes 0 there. We only have kinetic energy. So this kinetic energy at this position is given by half m. The velocity there is vt, v down square. So now if we equate these two energies at the up position and the down position, let's equate them because energy is always conserved. That's what we have assumed here, or rather, that's how the system behaves. We get half mvu square plus 2 mgr equals half m velocity down square. Now, what do we know about vu here? Let's calculate this for the minimum velocity situation. When the velocity is minimum also, the energies are equal. But we know that the Vu, the velocity minimum that's required in the up position, is given by square root of gr. Let's plug it in this equation. We get 1 by 2 m root gr square is nothing but gr plus 2 m gr equals half m velocity down square. Now, if we cancel out all the m's in this, which is common, and simplify, then what we get here is we get the minimum velocity at the down position. That would be equal to root 5 times gr. Because this half mgr and 2 mgr is nothing but 2.5 or 5 by 2 mgr. The 2 in the denominators would get cancelled. That's how we get 5 gr. So the minimum velocity at the down position would be square root of 5 gr. And the minimum velocity at the up position would be square root of gr. Thank you.